Welcome to Section 5, Lesson 9. In the previous lessons we covered specific function families linear, absolute value, piecewise, and generic functions through notation, evaluation, domain, and inverse. Today we add a powerful unifying tool, function transformations. The transformation toolkit applies the same 4 standard moves, shifts, stretches, and reflections to any function family, producing variants of the original function whose graphs are systematically shifted, stretched, or flipped relative to the parent graph. Mastering transformations once today gives you a universal grammar that works on every function family: parabolas, square roots, exponentials, logarithms, trig functions in later courses, and many more. Today we lock in the 4 transformations, the general transformation form, and the procedure for applying transformations or recognizing them from a graph. First idea on the board. The 4 standard transformations applied to a parent function f are: vertical shift up by k by adding k to the output, horizontal shift right by h by replacing x with x minus 8 in the input, vertical stretch by a factor of a by multiplying the output by a, and horizontal reflection by replacing x with negative x. Each transformation produces a new function whose graph is a systematic modification of the parent graph. The transformations can be combined to produce any rigid motion or scaling of the parent graph in the plane. The general transformation form combines all 4 moves into a single expression. G of x equals a times f of the quantity b times the quantity x minus h plus k. Reading the parameters, A is the vertical stretch factor with negative a producing a vertical reflection across the x-axis. B is the horizontal stretch factor with negative b producing a horizontal reflection across the y-axis. H is the horizontal shift with positive h shifting right and negative h shifting left. K is the vertical shift with positive k shifting up and negative k shifting down. Memorize the parameter meanings, and the general form lets you describe any transformation of any function in a compact expression. Third idea, the same transformation grammar applies to every function family. Vertex form for absolute value functions, a times absolute value of x minus h plus k is exactly the general transformation form applied to the parent absolute value function with b equal to 1. Vertex form for parabolas, a times the quantity x minus a squared plus k is the same. Square root functions, exponential functions, logarithm functions in section 13 all use the same transformation parameters. The universality makes the transformation grammar one of the most useful unifying concepts in all of algebra and pre-calculus. Function transformations apply standard modifications to a parent function f to produce a new function with systematically shifted, stretched, or reflected graph. The 4 standard transformations are vertical shift, horizontal shift, vertical stretch with possible reflection, and horizontal stretch with possible reflection. Combining them gives the general transformation form. Here is the general form. G of x equals a times f of the quantity b times the quantity x minus h plus k. Reading the parameters is the vertical stretch factor, negative a reflects vertically across the x-axis. B is the horizontal stretch factor, negative b reflects horizontally across the y-axis. H is the horizontal shift with positive h shifting right. K is the vertical shift with positive k shifting up. The order of operations inside is shift x by h, scale by b, apply f, scale output by a, shift output by k. Step 1 in applying transformations. Identify the parent function f and the 4 parameters a, b, h, k from the transformed expression. The parent is whatever function f appears at the heart of the expression. The parameters are read off the surrounding structure using the general form as a template. Step 2. Apply the transformations to the parent graph in the standard order. Horizontal shift by h, every point on the parent graph moves right by h units, with negative h moving left. Horizontal scaling by b, every point's x-coordinate is divided by b, compressing for absolute value of b greater than 1 or stretching for less than 1. Vertical scaling by every y-coordinate is multiplied by a, with negative A reflecting across the x-axis. Vertical shift by k, every point moves up by k units. Step 3. Identify key features of the transformed graph. The vertex or anchor point of the parent moves to the new location determined by the transformations. The domain may shift if h is non-zero, and the range may shift if k is non-zero. The arms or branches of the graph may steepen, flatten, or flip according to A and B. The interpretation of the transformed function is exactly the parent function's interpretation, modified by the systematic transformations applied. Here is the first worked example. Starting from the parent function f of x equals x squared, apply the transformations to produce g of x equals negative 2 times the quantity x plus 1 squared minus 3 and identify the 4 parameters and the resulting key features of the new graph. Step 1. Identify the 4 parameters by matching to the general form a times f of the quantity x minus h plus k with b equal to 1. Reading the expression a equals negative 2, h equals negative 1, because the formula has x plus 1 which equals x minus negative 1, k equals negative 3. Step 2. Interpret each parameter. A equals negative 2 means vertical stretch by factor 2 and reflection across the x-axis. H equals negative 1 means horizontal shift left by 1 unit. K equals negative 3 means vertical shift down by 3 units. Combining these 4 moves transforms the parent parabola into the new graph. Step 3. Identify the new vertex. The parent parabola has vertex at the origin. After horizontal shift left by 1 and vertical shift down by 3, the new vertex is at the point negative 1, negative 3. Step 4. Determine the direction of opening and the steepness. The negative coefficient on the quantity squared chunk reflects the parabola across the x-axis, so the new parabola opens downward instead of upward. The factor of 2 on the front stretches the parabola vertically, making it twice as steep as the standard parabola. Step 5. Identify the domain and range of the transformed function. Domain remains all real numbers because the parabola is defined for every input. Range is bounded above by the vertex I coordinate negative 3 because the parabola opens downward. So the range is from negative infinity to negative 3 inclusive at negative 3. Step 6. Verify by evaluating at a specific input. G of 0 equals negative 2 times the quantity 0 plus 1 squared minus 3 equals negative 2 times 1 minus 3 equals minus 2 minus 3 equals minus 5. The point 0, negative 5 sits on the new graph 1 unit to the right of the vertex, with the expected vertical drop of 2 units due to the steepness factor and the downward opening direction. So the transformed function is a downward opening parabola with vertex negative 1, negative 3, vertical stretch 2, and the standard parabolic shape otherwise. The big lesson from this example is the 4-parameter reading workflow. Identify a BHK from the formula by matching to the general form, interpret each as a specific transformation move, and combine them to find the new graph features. The same workflow applies to any function family, with the parent function f changing but the parameter interpretation staying identical. Here is the second worked example. Given a graph that looks like a V-shape opening upward with vertex at the point 3, 2 and arm slopes plus and minus 4, write the equation of the function in transformation form starting from the parent absolute value function f of x equals absolute value of x. Step 1. Identify the parent function from the shape of the graph. A V-shape opening upward indicates an absolute value function, so the parent is f of x equals absolute value of x. Step 2. Identify the parameters from the graph features. The vertex is at 3, 2, so she equals 3 and k equals 2. The arm slopes are plus and minus 4, indicating a vertical stretch by factor 4. The V opens upward, so A is positive, so A equals 4. Step 3. There is no horizontal stretch indicator on the graph beyond the arm slope, so B equals 1 by default. Horizontal stretch and arm slope both contribute to the apparent slope of the arms, but the convention for absolute value is to set b equal to 1 and let a carry the slope information. So a equals 4, b equals 1, h equals 3, k equals 2. Step 4. Plug into the general transformation form. G of x equals 4 times absolute value of x minus 3 plus 2. The expression captures the V shape with vertex at 3, 2 and arm slopes plus and minus 4. Step 5. Verify by checking a specific point. At x equals 4, g of 4 equals 4 times absolute value of 1 plus 2 equals 4 plus 2 equals 6. The point 4, 6 should sit on the right arm at 1 unit right of the vertex, with vertical climb of 4 matching the arm slope. Match. Step 6. Verify the symmetry by checking the mirror point on the left arm. At x equals 2, g of 2 equals 4 times absolute value of negative 1 plus 2 equals 4 plus 2 equals 6. The point 2, 6 is 1 unit left of the vertex at the same height as 4, 6, consistent with the V-shape symmetry. So the equation is g of x equals 4 times absolute value of x minus 3 plus 2. The big lesson from this example is the reverse direction workflow. Given a graph and a known parent function family, read off the transformation parameters by inspecting the vertex location, the direction of opening, and the steepness or slope. The graph to equation direction is just as common in homework and on tests as the equation to graph direction, and the same parameter identification skill works in both directions. 3 mistakes that catch every algebra student during their first weeks of transformation work. Each one is fixable with a small explicit habit applied on every problem. First mistake, misreading the sign of the horizontal shift parameter h. A student looking at f of x minus 3 concludes the shift is to the left by 3 units because of the minus sign, when the correct shift is to the right by 3 because the formula form x minus h has h equals positive 3 for x minus 3. The rule is counterintuitive. The sign of the shift on the graph is opposite to the sign in the formula. The fix is to find h by setting the inside of the parent function to 0. X minus h equals 0 gives x equals h, so a is positive whenever the formula has minus h. Second mistake, confusing vertical and horizontal transformations. A student looking at 2 times f of x reads the 2 as a horizontal scaling when the multiplication outside f is a vertical scaling. The rule is that anything outside f acts on the output and is therefore vertical, anything inside f acts on the input and is therefore horizontal. The fix is to memorize the inside versus outside convention. Outside f is vertical, inside f is horizontal. The convention is universal across every function family. Third mistake, applying the transformations in the wrong order, especially mixing the order of horizontal scaling with horizontal shifting. A student looking at f of 2 times the quantity x minus 3 confuses the order of the scaling and the shift. The general formula times f of b times the quantity x minus h plus k specifies the inside order as shift first by h, then scale by b. Both moves are inside f, but in the order shift then scale. Outside f the order is similarly fixed, scale by a first, then shift by k. Memorize the inside then outside order as the canonical interpretation. Function transformations are the unifying grammar across all of computer graphics, animation, signal processing, and any field where shapes or signals must be moved, scaled, or reflected systematically. 4 broad sectors below. In computer graphics, every 2-dimensional and 3-dimensional rendering relies on combinations of translations, rotations, reflections, and scalings of geometric primitives. The mathematical tools for these transformations are exactly the function transformations from today, generalized to multi-variable functions and represented as matrices. Game engines, image editors, 3D modeling software, and QA tools all run function transformations continuously during rendering, with the underlying math being precisely the Section 5 transformation grammar. In animation and tweening, smooth motion of an object across the screen is produced by continuously varying the transformation parameters between 2 keyframes. The starting position and shape are described by one set of parameters, the ending position and shape by another set, and the interpolation between them produces the smooth animation. Animation tools like Adobe After Effects and game engine animators use parameter interpolation extensively, and the underlying mathematics is function transformations applied to position and shape parameters. In signal processing, time shifts, amplitude scaling, frequency stretching, and phase reflections are all function transformations applied to the signal as a function of time or frequency. Audio editing, image filtering, and many other digital signal manipulations work through composing these standard transformations. The function transformation grammar applies directly because signals are functions of time or frequency, and the transformations are exactly the same ones we learned today. In calculus, function transformations interact predictably with derivatives and integrals. The derivative of a vertically stretched function is the same vertical stretch applied to the derivative. The derivative of a horizontally shifted function is the horizontal shift applied to the derivative with no other change. These predictable interactions let you handle large families of related functions through a single set of derivatives applied to a parent function. The transformation grammar is foundational to all of differential calculus and to many techniques in differential equations and physics. 3 things to take with you from this lesson today. Function transformations are the unifying grammar across all function families and across all of computer graphics, animation, signal processing, and calculus. First, the 4 standard transformations are vertical shift up by k by adding k to the output, horizontal shift right by h by replacing x with x minus a, vertical stretch by factor a by multiplying the output by a with negative a producing a reflection, and horizontal stretch by factor b by replacing x with b times x with negative b producing a reflection. The 4 moves combine in any combination to produce any rigid motion or scaling of the parent graph. Second, the general transformation form a times f of b times the quantity x minus h plus k captures all 4 moves in one compact expression. The same form applies to every function family: parabolas, absolute values, square roots, exponentials, logarithms, trig functions, and any others. Memorize the form and the parameter meanings once, and the transformation grammar transfers across every function family you will encounter for the rest of the algebra course and into calculus. Third, 2 sign conventions are worth memorizing carefully. The horizontal shift sign is opposite to what the formula appears to say. F of x minus 3 shifts the graph to the right by 3, not the left. And anything outside f is a vertical transformation, while anything inside f is a horizontal transformation. Memorize both conventions deliberately to avoid the most common transformation errors. Coming up next, the lesson called even and odd functions, where 2 specific symmetries identify functions whose graphs are mirror images across the y-axis or rotational symmetric around the origin. Even and odd properties are foundational classifications and have many applications in calculus and physics.